Okay, before we begin chapter 10, I kind of want to say what the point is first. So, we saw some examples of Galois groups. In particular, we saw that the Galois group of something like Q adjoin root 2 over Q is Z mod 2. That is, it has an identity element and then a non-identity element. And sigma squared, the non-identity element, is sigma, the non-identity element. When we square it, we get the identity. Okay, so it's isomorphic to Z mod 2, and the degree of the extension Q adjoin root 2 over Q is 2 certainly, which happens to be the order of the Galois group. We also saw that the Galois group of something where we add in an odd root, so like the cube root of 2 over Q, that was just trivial. It just has, well, I'll put equals. It just has the identity automorphism. In this case, the degree of this extension is 3, which is not equal to the order of the Galois group. Order is with absolute value bars. Okay, so observe that. However, if we compute the fixed field, I'm just going to call this gamma for now. Let's just call that gamma because I don't want to write that each time. If we compute the fixed field of gamma, what does the identity fix? The identity fixes everything. And actually, if we compute the degree of the fixed field of Q adjoin cube root of 2 over the degree of the fixed field, well, everything is fixed by gamma. So this is just the degree of Q adjoin cube root of 2 over Q adjoin the cube root of 2. And it's the same field, right? So that's a 1, which is the order of the Galois group. It is a 1. So we saw that the numbers did not quite work out in this example. But if we change Q to the fixed field of Q adjoin the cube root of 2 under the Galois action, then it does work out. And actually, in this case up here, this Q in this case, let's put it in orange, Q happens to be the fixed field of Q adjoin the square root of 2 under the Galois action, right? Because the Galois action negates the root 2 part, and so root 2 is not fixed by the Galois action, only the rationals are. So there's some numerology here that we're going to make very rigorous and precise in this chapter. This is the goal. So our goal here is to prove, at least in the finite case, that if you have L over K as an extension, finite, say, all of our extensions are finite, and gamma is the Galois group of L over K, then we're going to prove that the degree of L over K is the order of gamma. Sorry, not L over K. Sorry, L over the fixed field of gamma. Now it turns out, we will see later, so like in the next chapter, I believe, no, in chapter 12, in 2 chapters, that if L over K is normal and finite, there's Galois theory for infinite extensions, but that's not the scope of this class. Then it turns out the degree of L over K is actually, honestly, the order of the Galois group. That is, that the fixed field of gamma is just K. But that we'll get to later. In this chapter, we want to prove this result. That's where we're headed.